Okay, I'd like to take a little time and look at this particular reaction here, which is the reaction between calcium silicate, solid, carbon dioxide gas, going to calcium carbonate and silicon dioxide. This is just, seashells and limestone. This is sand. This would be carbon dioxide in the atmosphere, and this is found in a lot of rocks. So this actually represents a type of chemical weathering that occurs in rocks, and this actually ends up being important in the climate, because we know that carbon dioxide in the atmosphere tends to have a warming effect. So we're going to describe all of this in terms of chemical thermodynamics. And if I look at this reaction from left to right, what do you think delta S for this reaction would be? Let's see, delta S for this reaction. Is it going to be positive or negative? Well, I hope you're thinking negative, because we're going from gas phase reactant to basically solid product. And so that's going to represent matter that's free to move all over the place and be quite scattered, to matter that's contained in a particular spot. Now, since I notice that this reaction is reversible, that means it can go in either direction. Well, in order to be able to go spontaneously in this direction, let's see, if delta S is negative in this direction, that's going to be disfavored. So I better have, in the forward direction, that better be favored by the enthalpy. What's the sign of enthalpy if it's favored? Well, that's also going to be negative. So this reaction is negative for both entropy and enthalpy in the forward direction, and it's going to be positive. It'll just be the reverse. That's the way thermodynamics works. The reverse is just the opposite sign of the forward. So in the reverse direction, it's going to be positive both for the entropy and for the enthalpy. And this fact allows this reaction to get shifted depending on the temperature. And so let's see how this might work. Let's go ahead and calculate both delta H and delta S for this reaction. So I looked up the values for everything in a table, and we're going to calculate delta H for this reaction first. So let's see, delta H, that's going to be the final enthalpy minus the initial enthalpy. And my final enthalpies, that's going to be calcium carbonate, solid, and silicon dioxide, solid. So let's see, calcium carbonate, that's negative 1208. These are all kilojoules per mole. And I'm going to have to add to that negative 911. All right, so that's my final enthalpy. And we're going to subtract from that the initial enthalpies. So it's going to be the enthalpy of formation of calcium silicate. So that's going to be a negative 1635. And we're going to add to that carbon dioxide gas enthalpy, which is a negative 394. All right, we got to keep track of a lot of signs here. So let's see. I will be, let's see, this negative. Well, let me just do the math here. Hold on, let's see. Let's take, what's that, 394. Make it negative. And then I've got to add a negative, so I'll be subtracting 1635. So over here, this comes out to a negative 2029. But of course, I'm going to add that because I need to subtract this negative. So really, this 2029, that's positive. And then these are both negative, so we'll end up subtracting those. So minus 911 and minus 1208. And as predicted, right, in the forward direction, I predicted it was going to be negative, and indeed it is. It's going to be negative 90 kilojoules per mole. All right, let's do the same thing for the entropy. Let's find the change in entropy. So for the change in entropy, I want the final entropy minus the initial entropy. What's that going to be? Let's see, it's going to be calcium carbonate's entropy, which is going to be 85. And these are all joules per mole Kelvin. And silicon dioxide, oh, I messed that up, didn't I? Calcium carbonate is 92. And silicon dioxide, that's 41. That's my final entropies, and now I got to subtract my initial entropies, which will be 85 for the calcium silicate and 214 for the carbon dioxide. Now this math will be a little bit easier to do because everything's positive with entropy. So I'm going to start off with the positives. That's going to be 92 plus 41. And then I'm just going to subtract both of these, minus 85 and minus 214. Negative 166. And that's going to be joules per mole per Kelvin. We got to pay attention to these units with the enthalpy and the entropy. You got to make sure you do that. So yeah, that came out as predicted, right? We thought that the entropy would be negative, which we calculated it was, and we thought the enthalpy would be negative, which we've calculated that it was. Now what we want to do is we want to determine at which temperature does this reaction sort of go from being thermodynamically favored in one direction to the other. And before I do that, I have to figure out, okay, is this going to be thermodynamically favored at high temperatures in this direction or at low temperatures in this direction? So let me just think about this. So hold on. Delta G is delta H minus T delta S. And delta G negative, that tells me that it's spontaneous. So in the forward direction, let's see, I have a delta H is negative. And that, I'm just going to leave it there because at low temperature, right, if I just make temperature 0, at low temperature, this portion will be gone. Delta G will be delta H at a very, very low temperature. And so I see that delta G will be negative at low temperatures. So this reaction in the forward direction will be favored at low temperatures. All right, so what I want to find is at what temperature does it become spontaneous in the reverse direction? And we do that, remember, by saying, okay, we're going to set delta G equal to 0. And that's delta H minus T delta S. And if we add T delta S to both sides, I get T delta S is delta H, because of course it cancels over here. We divide both sides by delta S. And the temperature at which this becomes spontaneous in the reverse direction is going to be delta H over delta S. Okay, so I'm going to take my enthalpy change, and I'm going to make this, I'm not going to keep this kilojoules, I'm going to change it to joules. 90,000 joules per mole, because I needed to talk to this 166 joules per mole per Kelvin. And of course they're both negative, but when I do the division, those are going to cancel out. Joules cancels joules, per mole cancels per mole. I have an inverse Kelvin, so my temperature, my temperature will have units of Kelvin. So now I'm going to take my 90,000 and I'll divide that by 166. About 540 Kelvin. That's kind of hot. You know, it's hotter than the boiling temperature of water, for sure. But not, not like temperature of the surface of the sun, which is what's that, like 5,700 Kelvin. It's nowhere near that. So what that tells me is that this reaction is going to be spontaneous at low temperatures until it hits roughly 540 Kelvin. And at that temperature, at 540 Kelvin, or roughly, because this is an estimate, because all of these are for standard conditions, and we're messing around with the temperature a little bit. But anyways, at around 540 Kelvin, this reaction starts to be spontaneous in the reverse direction. Now, how in the world does this relate to the rock cycle and our climate? Well, at room temperature, at normal temperatures, there's going to be some calcium silicate rock that will be able to react with carbon dioxide in the atmosphere to give us limestone and seashell stuff and a bunch of sand. Now, when this stuff gets formed and it gets buried underground, well, all of a sudden, under heat and pressure, if it gets buried well underground, that temperature can rise. And then, therefore, this can start to occur in the reverse direction, say in the mantle or in areas of the earth under the ground where it's hot. And so under the ground or in other areas, if this gets warm enough, then the sand and the limestone can react to release carbon dioxide back into the atmosphere and also form some calcium silicate rock. So this reaction happens and has been happening on our planet for very long periods of time. And the fluctuation back and forth here can cause fluctuations in the amount of carbon dioxide in the atmosphere. And I bring this up because sometimes you'll hear people talk about, oh, well, how did the carbon dioxide concentration change in the atmosphere way back in the way back in the day when there were no humans around to emit fossil fuels? Well, here is one way that happened. Just a simple rock cycle. And so we see how fluctuations in carbon dioxide can occur just by the simple rock cycle occurring based on the temperature at which a reversible reaction can occur. And isn't that cool that we can understand some chemical processes that help us understand how carbon dioxide fluctuated in the past and how that carbon dioxide, which happens to warm the atmosphere and warm our planet, has an impact on the climate? I find that to be fascinating.